one system in physics that has potential energy is a pendulum. So we'll take a look at that here. I'm not sure how much you'll use a pendulum in the physics class you're currently taking, but pendulums have a few nice peculiarities about potential energy that we'll look at, so we'll go ahead and cover it here. So what a pendulum is essentially a nice rigid support, and then you have a nice long piece of string of length L like that, and there's a mass M at the end of the string. So there's a bob right there of mass M, and there's length L going down like that. And of course the way the pendulum works is you can grab this end here and pull it back, and the pendulum will start to swing back and forth like that. So kind of a bad animation, I know, but you get the idea. They're found in grandfather clocks, or maybe you even did a physics lab on them last time you took a course in science or something like that. So anyway, where does the potential energy come from? Well, the other thing I'll do in analyze the system is I'll put the ground all the way down here. And the reason why I'm doing this is because normally we're used to thinking of the ground as zero potential energy. So say when things like balls and things like that fall to the ground, we say they have zero potential energy, but we'll come to that in just a minute. So what we'll do then is we'll draw the pendulum then in some pulled back state. So the length L here of the string is going to be something like this. If I pull the pendulum back, then the whole thing is sort of going to look like this. So there's my red configuration, of course, but it's the same black pendulum bob all the way over there like that. Now you have to be careful right from the onset of your drawing that you wouldn't want to draw the pendulum bob all the way down here level with this one, because it's constrained by the string there. So remember, the pendulum is sort of always going to move in a circular arc as constrained by that string there, because the string always has a length L. So there's the L there, and now the string length is going to be an L over here. Now let's just say that you pull the pendulum back some angle theta relative to the vertical. So here's what I mean by vertical. This line right here, that's the vertical. And when you pull the pendulum back, well, by theta, that's how far you pull it back. So theta is equal to 0 would refer to a pendulum which has not been pulled back at all. Okay, so next thing you'll do then is let's see where the potential energy comes from. If I complete this right triangle right here and sort of draw a right angle right there, I can see right off that this is the length L right here, and that's the length L there, because those are the two strings, or the string that the pendulum is attached to. This side over here, in other words, just this distance right here, is going to be L times the cosine of theta. That's just the way that right triangle would work out. So when you look at it then, when the pendulum has been pulled from its equilibrium position all the way up to this position, how high has it been pulled back? Well, it's definitely in this little distance right here. This is how high the pendulum has been pulled back, and this distance right here is actually this distance, which is L, minus this distance, which is L times the cosine of theta. Now I can do a quick factor on that. I can write this as L times the quantity 1 minus the cosine theta. Now why did I want to find the distance the pendulum has been pulled back? Because the reason is because there's nothing super special about a pendulum other than the way it's just constrained on its string and its pivot point up there. But we'll remember, like, there isn't anything like there's some new definition of potential energy floating around. The potential energy of a mass, because it's pulled above the ground, is still the gravitational potential energy. Give it either the symbol U or PE. It's still going to be mg times h. But now remember, h is the distance above the ground at which the object has been displaced. So the simple example, of course, is if the ground is right here and there's like a ball right here, this distance h is how high the ball is above the ground, so that's how much potential energy it has. So we're interested then in how far the pendulum has been lifted above the ground. And if I do that number then, well, let's just see what we get out of that. How far above the ground? Well, this distance above the ground right here, let's just call it h naught, because that's the equilibrium height. So even in building the pendulum, to get it even to sort of survive like that, someone had to lift it up to this height h naught. But now when it's up at again a height h naught, it now gets displaced above h naught by an amount L minus cosine theta according to its pullback right here. So there's a couple of things you can do here sort of to work on this. You could say that the potential energy of the pendulum then, when it's been pulled back, is equal to the quantity mg times h naught. That's this potential energy because when it was constructed or built. But now you have to add in the additional height that has been lifted, which is an mgl times 1 minus the cosine of theta. So this would then be the total potential energy of the pendulum. Now there's something kind of interesting now, and this is why pendulums are nice here. I'll put a boxer on this, and this could be our result here, but we're actually going to work on it a bit more because there's a nice sort of concept about potential energy that we're going to talk about now. Where is the potential energy 0 for the pendulum? Now the first answer might be, well, when this pendulum bob here is back down on the ground. That's when mgh would be 0 and it's on the ground, and we like to call the ground potential energy equal to 0. But is that really the only case where the potential energy is equal to 0? Because If the pendulum is never allowed to break, like this string is never cut and so on, this pendulum bob here can never make it all the way down to the ground. It can never be down all the way down on the ground because it's a pendulum. It's connected to the rope, to the ceiling here. It can never be all the way to the ground. So it can never release this potential energy that it had to have because someone lifted it above the ground to attach it to the string. So what do you do about that? Well, what you do about that then is you sort of redefine where zero of potential energy is, because there's no reason for you always to carry around this potential energy. Let's just call this potential energy due to the construction of it, or something like that. If someone had to lift the pendulum into place, we don't need to carry that around in every problem we work. We know someone had to lift it. Maybe it was very heavy. Maybe it required a forklift or whatnot. But the point is that now that it's a pendulum, it's never going to lose this potential energy because this string is never going to break. So why not just get rid of it? Why don't you just redefine where potential energy of zero is going to be? So it's not convenient for pendulums to say the ground is potential energy is equal to zero. What's actually more convenient is to say that this level right here, that red line right there, is where potential energy is equal to zero. And if you do that, then you can say when the pendulum's in its lowest spot right there, that's where it has zero potential energy. And it even comes from the equation we already got just by sort of getting rid of that part right there. But instead, if we say something like potential energy is just mg times L times 1 minus the cosine of theta, this is the potential energy of a pendulum. And this is all you sort of need to know about it. So you can just put a big box around it and say, there you go. Now, does the zero bit work out? Well, yeah, because if the pendulum is over here in its straight vertical position, theta is equal to zero. And if theta is zero, the cosine of zero is 1, and 1 minus 1 is equal to 0. This term would be 0, so the potential energy would then be 0. So in this particular case, then, we define the zero energy of the pendulum to be right there where it says lowest spot. And one last thing about potential energy, then, which is sort of nice that the pendulum brings out. I'll just do a quick drawing there because the board is getting a bit crowded. So here's the pendulum once again back. Here's that heavy support at the top. Here's the pendulum down here, and just say it's sitting down here like this. So there's that pendulum bob. It's sitting down there. It hasn't been displaced. Now remember what the definition that we think of when we hear the word potential energy. What do we think of here? So potential energy, we have another video that sort of discussed this here. Ability to do something. And that something there is some action. Textbook aficionados have some things memorized, maybe from another class, will say the ability to do some work, although it's kind of hard to know what that actually means. So, think of the pendulum now in this total equilibrium position. It has not been pulled one way or the other. We say potential energy is the ability to do something. Can a pendulum, which is just hanging in this position and not being displaced one way or the other, does it ever have the ability of doing any work or any action? Can it ever do anything? I say the answer to that question is no, because the pendulum is just sitting here. It can never do any work. It can't swing to the side to hit something because it's just sitting there at equal to 0. At theta is equal to 0. So why not just call this configuration potential energy equals 0? Because in this configuration, unless someone comes up and moves it, it has no ability to do something. It cannot do any work. It can't get going to do anything. So it's just going to sit there like that. That's another reason why we like to redefine the 0-point potential energy of a pendulum to be when the pendulum's at its lowest spot, not arbitrarily above some ground which is down here, which has to be reminiscent of, say, the contractor who came out and lifted the thing a high H0 force to get it up into that configuration. We just don't need to worry about that. We're concerned more with when can the pendulum actually do something, and when it's in this configuration, unless it gets moved, it can't do anything. In other words, a pendulum that's just sitting here like this would just stay like that forever, unless someone comes up and cuts the string, in which case there would no longer be a pendulum. So anyway, so there's the potential energy of a pendulum. MGL times the quantity 1 minus cosine theta, where theta is the angle you displace it from the vertical. And there's some nice other nuances about potential energy in there.